Hello and welcome to my presentation on our paper, Image Conditioned Diffusion Models for Medical Anomaly Detection. Now, if you don't have time to watch the full video, here's a quick summary. We, in our method, localize anomalies by generating an anomaly-free version of an image using an image-conditioned diffusion model. Why are we using image conditioning? Well, by conditioning the diffusion model on the input image instead of noising it, we don't have any loss of information. That allows it to better attend to the healthy regions and maintain them. During training, we can also use this conditioning mechanism to train the model to correct images with synthetic anomalies introduced into them. That better helps the model learn to change the unhealthy parts and maintain the healthy parts. That means that when we compare our restored image with the input image, we can use the difference measured by SSIM to localize anomalies. Now, if you've got a bit more time, let's go into some background. Reconstruction-based anomaly detection is the predominant method for medical anomaly detection. It involves training a generative model on a healthy distribution of images, using it to reconstruct an image at test time, and comparing the difference to localize anomalies. Historically, this would be done by using a VAE or a GAN. More recently, diffusion models have been the go-to generative model, so they've also been becoming more common for anomaly detection. So if you look along the bottom row, the way you'd apply a diffusion model would be by taking your input image, partially noising it, not fully, only partially, and then using the diffusion model to try to sort of reverse that noising process, but correcting unhealthy or anomalies while doing so. And that's pretty cool. But regardless of whether the model is a diffusion model or a VAE or a GAN, all of these reconstruction-based methods rely on some common assumptions. Those assumptions are that models trained using only healthy data are both unable to reconstruct anomalous features and capable of reconstructing normal images. Unfortunately, these assumptions often fail, which is what we're going to try and address in our method. So, as I mentioned, in our method, we condition our diffusion models on an input image and use that to generate a pseudo-healthy version of it. To localize the anomaly, we measure the difference with the structural similarity index measure. That is the difference between the restoration and the original. Now, during training, we use the healthy image as the target for the diffusion model, while we condition on the same image, but with a synthetic anomaly introduced into it. Okay, so how does this help us guarantee those assumptions? Let's break them down. Well, to start with, we ensure the assumption that models trained using only healthy data are unable to reconstruct anomalous features, as we are training the model explicitly to correct anomalies. Because at training time, it was trained with images with synthetic anomalies in them to produce the healthy version. We also ensure the assumption that these models are capable of reconstructing the normal areas of the image. The reason we strengthen that is that our input image is not noised or compressed during this process. So in a diffusion model based method, it would be noised. In a VAE based method, it would be compressed. Here, we're giving it full access through the conditioning. And that allows this diffusion model to correct and maintain the healthy areas. To show you some results from this, we evaluate our method across 4 different test sets, and we achieve high pixel level performance on a variety of types of anomalies. Large hyper-intense ones, such as those in Brat's T2, small hypo-intense anomalies, such as those in the Atlas dataset, and tiny scattered anomalies, which are particularly hard to catch, such as those in the DDR dataset. But not all of our results are amazing. Specifically, we struggle on low contrast anomalies, such as those in Brat's T1. And that's because we are doing our comparison in pixel space as a sort of traditional reconstruction-based method. And when there's low contrast between a healthy tissue and the anomaly, a pixel space comparison is always going to leave sort of a smaller difference. So this could be improved by moving the comparison to feature space, but we leave that up to future work. So to briefly recap the summary I gave at the beginning, in this method, we are localizing anomalies by generating a anomaly-free version of the image using a image-conditioned diffusion model. Why are we doing that? Well, it's because we don't want to lose any information through noising and compression. And we also want to be able to train our model explicitly to correct synthetic anomalies and any anomaly at test time. Thank you for listening. That's all from me. I hope you enjoy our paper and our poster. Thank you.